Another example, let's say we have this robot, which is a hopping robot. So it has a leg, a body with the mass of m, and also a spring, and also a toe. We have a lumped mass here, let's call it toe. So it is jumping up and down, it is making contact with ground, and it is jumping up. And also, let's say we have an actuator here, from the hip to this end of the spring. So the actuator is controlling this distance. Let's say the distance is u, and at this time ut. So we have a computer, let's say, which is controlling this ut. So it can increase this distance or decrease it. So if you look at this system, you're gonna notice we have 2 degrees of freedom, right? I need one variable to show the location of this body, maybe the hip of it, and also another variable to show the location of this lumped mass or toe. You have a lot of different options, but I'm going to choose the distance from the ground to the hip, this height. I'm going to call it y1, and also the distance between this lumped mass or toe from the ground, I'm going to call it y2. And then because we have 2 degrees of freedom and I'm using 2 coordinates, I'm not going to have any constraint equation, right? So let's say the length of the spring, on a stretch length of the spring, is L0 as well. So the compression of the spring, or let's say the extension of the spring, how much we are stretching it, it's gonna be y1 minus y2 minus this u minus the initial length of the spring, right? So delta, or the extension of the spring, is gonna be y1 minus y2 minus u minus the initial length of the spring, L0. So it is stretched this much at any time. Now, knowing that it's stretched, I'm going to be able to draw the free body diagram of any of these parts. Let's start with the toe. We have gravitational force, mg, and also we have spring force. So if it's stretched by delta, the spring force is going to be k times delta, right? And also, whenever it touches the ground, we are going to have a force from the ground as well. So I'm going to put a force here, and let's call it Fg, F from the ground, which is going to be 0 when y2 is positive. But we are going to have some force here. Fg is going to be non-zero when y2 is 0 or negative. I'll come back to that later. So this is the free body diagram of the of this mass, and the only Newton equation I can use here is sum of the forces in the vertical direction is equal to mass times acceleration in that direction. So in this direction, I'm gonna have m times y2 double dot is equal to sum of the forces. We have mg downward. So this is my positive direction, so the force from the ground is going to be negative. Then the force from the spring, it is positive k times delta. I can write all of this, or I can just write delta for now, but we know delta is this. And plus Fg, force from the ground. And the force from the ground, if I want to finish it, is going to be equal to 0 if y2 is more than or equal to 0. And it's going to be some force from the ground if it's not, if y2 is less than or equal to 0. People have different ways to model the ground, but one of the well-known methods to model the ground is modeling the ground with spring and damper. So if it penetrates just a little bit into the ground, we are going to have something, a force which is like a spring force, which is going to be a constant number times the magnitude of penetration into the ground upward, so to push it away. And similar way, we are going to have another force from the ground, which is going to be proportional to the velocity of penetration to the ground, like damper. So when Fg is going to be equal to a constant, a spring constant, I'm going to call it Kg, a spring constant of the ground, times y2. And this force must be positive whenever it penetrates, right? But if it penetrates, y2 is going to be negative, so I'm going to put a negative number here, which means it's going to be upward, because y2 is going to be negative, right? And in the same way, a damper constant, I'm going to call it Bg, the damping constant of the ground, times y2 dot. So whenever y2 is less than 0. Okay. It doesn't matter actually, put the equality here or at the top. Both of them are going to give you same thing. So this is going to be the equation for the first mass, and it is in the form that we want for the simulation, right? Y double dot is a function of y1, y2, and also the input, right? So we have everything here. And we can write the same thing for the bigger mass. If I want to draw the free body diagram of it for the body of the robot, we have gravitational force, and also we have force from the spring, right? Which is going to be the reaction of this force. So it's going to be downward, K times delta. And in the same way, sum of the forces in the y direction is going to be equal to mass times acceleration in the y direction. So m times y1 double dot is going to be equal to negative mg, because it is downward, my y1 is upward, and minus k times delta. And we are done. We found all the dynamical equations. Again, if you start from the beginning, at the beginning, I know all the initial conditions. I know what is y1, what is y2, what is y1 dot, and y2 dot. So if I put those initial conditions, I'm going to be able to find delta. After finding delta, I can calculate y2 double dot, and here I can calculate y1 double dot. So I can integrate y1 double dot, y2 double dot twice to find y1 and y2 and also their derivative in the next time iteration. Then repeat the whole thing again for the next iteration. That's going to be the integration, right?